Hello, everyone, and welcome to my talk. I'm Joseph Allingham, a PhD student at Sydney University, and I am going to tell you how I modeled electron clouds of galaxy clusters with strong gravitational lensing. So our goals here were to model the density distribution of a galaxy cluster to understand the relationship between the electron and gas density and the dark matter density, and in fact connect the two and to deduct the electron distribution from the lensing reconstruction. So just a few words about lensing. So when we look at a distant galaxy and it happens to be in the background of another galaxy cluster, the foreground one behaves as a gravitational lens. That is, its general relativity effect is to curve the path of photons of the background cluster, and it can appear to us as several distinct images. So a few words now about data. So I used the MUSE cube as spectroscopic data to analyze the background galaxies, that is the quasars, and the HST and DES data for the foreground galaxies. Um, as for the X-ray, I used the XMM neutron data. So we studied two galaxy clusters, MAX J0242 and 0949, at redshift between 0.4 and 0.3 pardon, and zero point 0.4. And I should really outline the former cluster is way better constrained than the latter because we detected 6 systems of multiple images. So that is 6 background sources, quasars, that allow us to constrain the mass distribution. Um, we also use this density profile, the dual pseudo-isothermal elliptical matter distribution that you can see here, and not an NFW, although we did check the validity of our reconstruction with respect to NFW. So now the reconstruction itself. So on the right here, you can see an HC image of MAX 0949. And in white, you can see the equipotentials, the gravitational potential. And this reconstruction is provided by the software Lenstool, which through an optimization of the general relativity equations finds the best model. So here you have about 80 galaxy potentials that are being optimized on top of a dark matter halo potential. And in green, you can see the potentials, the most important ones. And in red, you can see the X-ray data. So we can observe that the X-ray data don't have exactly the same ellipticity as the gravitational lensing reconstruction, but the profile is basically the same. Now that we have this reconstruction, well, let's compare it to X-ray. So in the case of 0242, the reconstruction can appear to be worse because the RMS is larger, but actually it's just due to the fact we have more systems to constrain the data. This cluster appears to be relaxed and cool core, while its counterpart 0949 actually probably post-merger is not absurdly disturbed, but is not quite cool core neither. And we will have to keep that in mind in the rest of our analysis. If we now do the full reconstruction for each clusters, we can observe that the dark matter halo, DMH, and brightest galaxy cluster, so the main central galaxy, contributes for almost all the density. Well, the full density, right? The dark matter and the baryons. And of course, the dark matter is a key aspect here as it is about 85% of the total mass. And comparing these to the X-ray data, we find, we could say, a quite good agreement. So these are coming from XMM neutron, and they were fit by NFW in cyan, while our DP IEMD potential was fit by another NFW in purple. If you can't distinguish the two on the left plot, it's just because they are completely identical. And on the right one, we still find the agreement to be very good. So I want also to outline this is a 3D reconstruction. Of course, this makes assumptions because neither the lensing information nor the X-ray are three-dimensional in this case. We are actually preparing an article on all of this gravitational lensing reconstruction. Um, and now let's talk a bit about the electron cloud before we connect the two. So a common assumption is that the electron cloud of galaxy clusters is traced by the dark matter halo, and we can basically neglect other galaxies. We will investigate that. We also want to investigate the X-ray and Sunyaev-Zel'dovich effects because these trace the electron density. So just a few words about SZ. SZ is the inverse quantum scattering of background CMB photons that would come to hit the hot electron gas of the galaxy cluster. And this actually broadens the spectral line and shifts the photons, so they're not all at their initial CMB frequency. So we can observe that sort of spot on the sky. So we have a direct probe though of dark matter, so we can take the reverse path as what people usually do. We can develop a model to reconstruct the electron cloud and therefore predict SZ and X-ray just using the lensing. So there are key aspects here. Physically, we want to develop a model that is very explanatory of galaxy clusters with the thermodynamics, the baryons, and the dark matter distribution. We also want to connect all of that, and as we do have, well, simplify, I said the dark matter, but the full matter density, we can relate the baryon distribution to that of dark matter instead of doing the contrary. And we can also, in a possible future, test deviations to our models to detect, well, normalizations, but more interestingly, maybe to detect or constrain dark matter. So what people usually do is they use these classical, so to say, profiles, the beta profile for the electron density, and the polytropic law for the temperature of the electrons. So in the literature, there are tabulated measurements of beta and gamma, but these can vary a bit. However, as a baseline, we could take these values. What we want to do now is to use the core radius we found in our lensing analysis and put that in the electron density. We would need a temperature normalization, which is given by the X-ray analysis. So it's not fully lensing yet. And also an electron normalization, which we will come back onto. We will also keep for the moment gamma as a constant, but try to optimize the beta index. So just to understand why the X-ray and SZ effect are connected to the electron density, it is simply because of these formulae. So in red, you can see the place where the electron density and the electron temperature come in to be important. So these are simple maps that we created with these models. I'm going to explain a bit more how, but you can see that the ellipticity traces that of lensing, of course, and the core radius also is coming from lensing. So there is a missing parameter here, though, if we want to use lensing to infer the electron distribution. With these canonical classical models, and that is the electron distribution. pardon me, it's the electron distribution coming from the gas fraction. So the gas fraction Fg actually is a key ingredient here. And as we understand it, there is no universal law to describe the gas fraction, but that's what we want. So I took the XCOP data plus the X-ray analysis of the XMM data for our two clusters, and was able to, well, to fit quite well, even I would say very well, the data to the model I propose here. So I call it the arctangent model, and I must outline that all parameters are known. A, B, RC, RF are either coming from lensing or from a universal parameter. And it's very interesting also because an arctangent model will converge for r tends to infinity. And here, a few comparison of the different models we use for the gas fraction. So we try to fit the yellow X-ray data to a power law. But the problem of a power law, of course, is that it never converges. And we want, at very large scales, our gas fraction, the cumulative one, to converge towards the Fg infinity value. That is the pardon me, the universal baryon fraction corrected uh, by the local depletion factor and the stellar fraction. And we can see here that the arctangent optimization for this particular cluster in red works outstandingly well because it's completely within the margin of error. As for our universal arctangent model, it is not entirely, but we still can be quite happy with that. I think this is one of the worst examples of all 14 clusters analyzed. So I would tend to say this model can be so far understood to be universal, at least for relaxed and relaxing clusters. So now we have the classical models on the electron density and electron temperature and the gas fraction. So from that, we can, from the full matter density, completely predict the X-ray and SZ effects. So we can compare our model to maps. And we actually did that for X-ray, not quite yet for SZ, this is coming. But we were able to fit very well an optimization with three parameters, two parameters optimized with just to check if they actually are in line with the lensing information, and they are. That's what the right plot is telling us. And the beta exponent that is also being optimized here and actually matches quite well the values that are commonly found. We also found that the double beta model proved to be just as efficient as a simple beta. And this is an example on how the electron density traces the dark matter halo, at least in our case and with our lensing analysis. So all of this works together. The observations are matched. So one can still wonder, isn't there a way to do something better? Because we had to optimize beta, and it's a somewhat universal, but not really parameter. The polytropic index is somewhat universally a constant, but not really. But with Dominique Eckert, so credits to him, a universal model for the polytropic index. So with this relationship, there is a universal description of the electron temperature, knowing that T naught is a normalization constant that is known universally. And so it's a quite complicated equation, but with this, if we know the electron density, we know the full temperature. And as it happens, we can write the Poisson equation. So we have to make the hypothesis, though, that we are applying the very old theorem here. But with the Poisson equation applied on the gas, but it works just in the same way. We can derive the electron number density from that. We get a fully analytical solution. I can't stress enough how important this is, because just knowing raw m on the right hand side and the expressions, theoretical universal expressions for the density of the gas and the temperature of the gas, or those of electrons, we get that full reconstruction. So I must here present to you the math for those who like math, but I must at the same time stress how important this is, because we can completely describe a cluster just through lensing. So there are limitations though. Our clusters are either relaxed or relaxing. And in that latter case, we can wonder how good our model is. However, we have not yet applied and don't think we can quite apply this model to perturbed geometries just because the virial theorem will not apply. We also only have 2 lensed galaxy clusters so far. So the rest of the analysis was performed with more objects, but on that we have to admit that's very limiting. As for the so some parameters were assumed to be constants as the metallicity. We also use some normalizations that are supposed to be universal, but there might be a bit of variation, of course. However, I have to stress that there are ways to rescale the relationship presented earlier, the fully analytical electron density relationship with a known density. So, for example, if instead of knowing the temperature normalization, we knew the electron density number, the electron density normalization, we could still apply the same formula just as efficiently, or if not more. So I think this formula has a lot of potential, as you might be able to say. So what we've done, we have offered a new original gas fraction model that should be useful for anyone who still wants from X-ray and SZ1 to derive some information about dark matter halo. More importantly, we have presented that fully analytical derivation of the electron and gas density from the full matter density, and from basically just the observation of strongly lensed objects. And well, we also have found that the classical models used by the X-ray and SZ community, the all Viklin derived potentials, the most simple of which is beta, are in good agreement with what we were doing. So we have that sort of intermediate step that allows us to say that we are not doing crazy science. On a longer term, we could hope to constrain dark matter models, and in particular interacting dark matter, if there were deviations to our models. So there are 2 publications to come on that, and you can find me on my ORCID page, and you can email me about all this if you're interested. So stay tuned for the papers to come, and goodbye.